Okay, we're going to finish out with two more examples of related rates problems. This time we're going to move from cars to airplanes. So an airplane flies at a constant altitude. So that means it's not moving up or down. Constant altitude of 4 miles toward a point directly over an observer. The speed of the plane is 600 miles per hour. Find the rate at which the angle of elevation between the observer and the ground is changing the instant the airplane is 5 miles from the observer. So we might have to read that last sentence there a few times, but let's see if we can figure this out. First of all, we'll assume the ground beneath the airplane, there's a certain level ground here where the observer would be observing from. I mean, there might be hills and everything, but we'll just assume the observer is right here. So here's our observer. We'll just draw a little stick person there. There's our observer. And then coming right, the plane is flying toward a point directly over the observer. So if I were to come up directly overhead from the observer, some point that was obviously, 4 miles above. Right, that's the plane is flying towards that point. So we're going to draw the airplane over here at the same height. And you're probably a lot better drawer than I am, but I'm going to draw a little airplane here. Okay, with my wings and my exhaust. There's my big airplane. Now, it's not drawn to scale, so keep that in mind with this 4 mile height above ground. But literally then the height from this distance from the airplane to the ground, that's constant, 4 miles. That's not a variable quantity. Okay. But and we know that this airplane is flying at a constant speed, right? 600 miles per hour. Put that direction to give us perspective. So the question is, find the rate at which the angle of elevation between the observer and the ground is changing. So let's draw. What is the angle of elevation? Well, as the person's looking at the airplane, right, there's some angle of elevation here. Some angle of elevation here that we see. And if we draw a line from the observer to the airplane, that angle there is the angle of elevation. Now, is that angle constant or is that angle changing? Well, think about it. As this airplane flies towards the observer, that line connecting the airplane to the observer is changing, and so that angle is getting bigger, right? It's getting closer and closer to 90 degrees, right? When the plane is directly overhead, it's 90 degrees. Let's call that theta. Okay. And then, so basically we can talk about what rate is given and what are we asked to find. Well, the speed of the plane is given. That's a rate of change, right? 600 miles per hour. But what is changing here? It's really, if you think about the distance from the airplane to this point right above the observer, another way of thinking about that distance is if I were to look at where the plane is horizontally, right down directly beneath the nose of that aircraft, right down here. Now here's the shadow of the airplane, assuming the sun is directly overhead. Right, this point right here, which is the point on the ground directly below the airplane's nose, right? That point's going to move as the plane flies this way, and so we can think of that distance from the airplane to the point directly above the observer as the distance from the observer to this point right here. That distance is changing; it's getting smaller. Let's call that x. And in fact, that's what's given. We are given the rate of change of x with respect to time, and it's 600 miles per hour, which is the speed of the airplane, right? This point will be moving at 600 miles per hour. But think about the value of x. Is dx dt going to be negative or positive? Think about it. What's happened to x? It's getting smaller. Since x is getting smaller, dx dt has to be negative. Right? As time progresses, that distance between the point on the ground, right, directly below the airplane, and the observer, that distance is going to get smaller and smaller and smaller. What are we asked to find? The rate of change of this angle of elevation. That's d theta dt. And we're asked to find it when when the instant what? The instant the airplane is 5 miles from the observer. Okay. 5 miles. Is that the value of x? Is that the distance from the observer to the airplane? Is that where the airplane is, on the ground? No, the airplane's up here. What's the distance from the observer to the airplane? What's going to be the length of this dashed line? Right? That's the distance. So is that distance fixed, or is it changing? The answer, it's changing. We'll call that L. That length of the distance between the observer and the airplane. Right? As the plane gets closer and closer, that distance. In fact, when the plane becomes directly overhead, then L goes to 4 miles. So L is getting smaller, getting closer and closer to 4 miles as the plane goes directly to that point directly above the observer. Well, we've seen this a lot, right? Do we see a right triangle here? Sure do. And that's going to be helpful, right, for us to find the relationship. So we're going to find d theta dt when what? When the distance between the airplane and the observer, L, is what? 5 miles. What's the relationship between the variables of interest here, x, theta, and L? Well, we can use one of the trigonometric functions and look at the ratio. But if you think about it, I said between x, theta, and L, really all I know is dx dt and d theta dt. I don't know dl dt. Find dl dt. Since it's only between, since we only know dx dt and d theta dt, I want to think, is there any way just to relate theta to x only and kind of forget about L for a little bit? And the answer is yeah. What function will relate what theta to x and 4, right? Which is this length. Well, that's what? The opposite and the adjacent side lengths. The opposite and the adjacent side length. So I'm going to use tangent. My equation is going to be tangent of theta. Tangent of theta is the opposite, which is 4, divided by the adjacent, which is x. Now, before I take the derivative with respect to time of this equation to get my related rates equation, look at this 4 divided by x. Do I have to use the quotient rule on this? The answer is no, because I can rewrite this. This is 4 times x to what power? To the negative 1. So now I don't have to use quotient rule. I can just use power rule. Of course, I've got a chain rule, right? When I take the derivative now with respect to time of both sides, I've got a chain rule. So here, the outer function is tangent, inner function is theta. What's the derivative of tangent? Do you remember that? Secant squared. Derivative of tangent, secant squared. Theta times the derivative of what's inside. What's the derivative of theta with respect to t? D theta dt. And that's what we're looking for, by the way. That's what we're asked to find. Over here, derivative of 4 times this. 4 is a constant multiple. I can pull that out. Times what? The derivative of what's inside, or what we have here, x to the negative 1 rather, is chain rule again. The outer function, x to the negative 1, derivative is what? Negative 1 times x to what? Subtract 1 from negative 1, negative 2, times the derivative of the inner function, dx dt. So that's chain rule. There's my related rates equation. Now, can I begin plugging in now? Don't plug in any values that we know yet. Now, it's interesting. What I need to find is secant squared theta here. I'll need that. D theta dt and x and then dx dt. Of course, I know what dx dt. That's given, so I can replace dx dt with that. What about x? Let's talk about that. What about x? How do I know what x is? I know what L is when I want to find d theta t when L is 5. Well, what is x at that instant? Well, if you look here, x and L are related by the Pythagorean theorem. Notice the right triangle, x squared plus 4 squared is L squared. And so when L is 5, I can plug in 5 for L. I get x squared plus 16 equals 5 squared 25, or x squared is equal to 9. And so clearly x is 3 miles at that instant. X is 3. What about secant theta? Do we know what secant theta is? Yeah, remember cosine of theta is the adjacent side length, which is x, over the hypotenuse L. Adjacent over hypotenuse. What's secant theta? It's the reciprocal. It's the hypotenuse over the adjacent. So secant theta is just L divided by x. But at that instant, what is L? 5. What is x? We just found it. 3. So secant theta is equal to 5/3. So I'm going to plug all this information in here. And what do we get here? Secant squared theta. Remember that's secant. Right, this is secant secant theta squared is what that means. What is secant theta? Secant theta is 5/3 at this instant. So this is 5/3 squared times d theta dt. And here I've got, of course, what does this come out to be? This is -1 divided by x squared, right? Negative x to the -2. So I've got a 4 here. So -4 over x squared. What's x? X is 3. Times dx dt. What's dx dt? Dx dt was given -600. Okay. So we now can solve for d theta dt. We've got a little bit of arithmetic to do here to clean things out here. Let's do that. So if I square this, I get 25 ninths d theta dt equals, negative times negative is positive. I get 9 down here, so I get 4 ninths times 600. So negative times negative is positive. And then how do I solve for d theta dt? Multiply by the reciprocal, which is 9/25 times 4 ninths. I see some 9's cancel there. Right? 25 goes into 600 how many times? $25 goes into 100 4 times. So 600, it will go 6 times 4, 24 times. Four times 24, 96. What are our units here? Do you remember we did some units involving angles, right? Rates of change of angles. Remember our time units here, real important, are not seconds. What are they in? Our rates are what? Miles per hour. So our time units are hours. And remember what we said about d theta dt? It's not degrees per hour, but it's going to be radians per hour. Now, think about the fact that it's positive 96 radians per hour. That means the d theta dt being positive means theta is increasing as time progresses. Theta is getting bigger. Is that true when we look at our diagram? Is it indeed true that theta is getting bigger as that airplane flies closer and closer to being directly overhead? Yes, it does make sense. It does make sense. Okay. So quite a lot going on there. We've progressed quite a ways from the initial example we did. We'll do one more like this with an airplane a little bit differently. So let's go on to that. This time we have and this is a pretty practical one, I think. An airplane is flying on a flight path that will take it directly over a radar tracking station. It's kind of like the problem we just did. Instead of an observer, we're going to fly directly over a radar tracking station. So we'll draw our tracking station here. It's got one of these radar dishes right on the roof that it shoots the signal up to the airplane. Here's my airplane again. Draw me another airplane. And it flies at a constant altitude again. Man, sounds familiar. So this time the altitude is 6 miles. So the height from the ground up to the aircraft is 6 miles, and that's constant. Again, that plane is going to fly at that constant direction. It's not going to be flying directly towards the radar station, right? It's going to maintain that constant height. And it's going to take it out. It's going to take it on a path directly over the radar tracking station. So the distance between the airplane and the radar station is changing at a constant rate of 400 miles per hour. What's the distance between the airplane and the radar station? Well, it's going to be this, right? This dashed line distance right there. Okay, is that distance constant or is that changing? You know, it says it's changing here in the statement, but clearly it is. It's getting closer, right? As time progresses, that distance is getting smaller. So we're going to call that length L. And then again, we have the fact that that distance is changing at a constant rate. What's the speed of the airplane? Okay, so how fast is the airplane going? And this is really a good problem because, you know, when radar stations are tracking aircraft, how do they know how fast the airplane is going? What they do is they'll send a signal up to the airplane. It will bounce off the airplane and come back, and they know how fast that signal goes, and so they can time it takes to go from the radar station to the airplane and come back down. They can time that, and so as they know how fast it's going and they know the time, they can find the distance. And of course, they're sending that signal out very rapidly, many times, and so they're constantly getting updates about this rate of change of the distance between the radar station and the aircraft. But how do they know how fast the airplane is going? Because unless the airplane is flying directly towards them, right, then DLDT is not the speed of the aircraft. So we're going to use calculus to show you how to do that. So again, I'm going to look at the point directly beneath the nose of the aircraft on the ground here. And again, it's like the last one we just did. The distance from that point to the radar station is getting smaller again. I'm going to call that x. Okay. And so it's very similar to the last problem we have in a lot of ways, and I see my right triangle here. This time I'm not interested in the angle right here, but I'm interested in these quantities x and l and how they change. And so actually what we're given here is that the distance between the airplane and the radar station is changing at a constant rate of 400 miles per hour. So that's dl dt. That's 400 miles per hour. Now, is that positive or negative? Well, think about the value of L. Is that getting smaller or larger as time progresses? Is L getting smaller or larger? It's getting smaller. dl dt is negative. What are we asked to find? What's the speed of the airplane? What's the rate of change of what? What's going to tell us the speed of the airplane? The answer is, as this airplane flies, right, horizontally at that fixed altitude of 6 miles per hour, this x length, the distance from the point on the ground beneath the nose of the aircraft to the radar station, that x is going to change at the same rate as the speed of the aircraft. So we're going to find dx dt. And we're going to find it when what? The instant that what? The airplane is 10 miles from the radar station. 10 miles from, so is that L or is that X? When the airplane is 10 miles from the radar station. What is the distance from the airplane to the radar station? From the airplane to the radar station. That's L. That's L. So when L is 10 miles. So what's the equation of interest here? Equation of interest comes from the Pythagorean theorem. We've got this side length squared plus this side length squared, which is fixed at 6 miles, equals the square of the hypotenuse. Of course, 6 squared is just 36. So when I take the derivative with respect to time, we've seen this so much now, I think we know what happens, I hope. The derivative with respect to time of x squared is 2x times dx dt. What's the derivative with respect to time of 36? 0. It's a constant. And this is 2L dl dt. So I'm trying to find dx dt. I'm going to solve for dx dt by dividing both sides by 2x. So dx dt is 2 divided by 2. Those 2's cancel. You can see that, right? And I get L divided by x dl dt. And there it is. I have my related rates equation. So how can I find out what dx dt? I need to know what dl dt is. I know what that is. That's given. I need to know what L is. I know what L is. That's 10 miles. And I need to know what x is. Uh-oh, how do I find x? Well, at the instant L is 10, I know this relationship holds. And so when L is 10, I've got this equation, and I can solve for x. In this case, if you solve for x is equal to 8. X is 8 miles at that instant. Check and confirm that. And so this information tells me that dx dt at the instant L is 10 miles is L is 10, x is of course 8, and dl dt negative 400. Of course, notice the units here. 10 is in miles, right? And x is in miles as well. Miles divided by miles, that's unitless. And this 400 is what? Miles per hour. What are we going to get for the rate of change of x with respect to time? It's going to be in miles per hour. 10/8 times 400 is 500. And notice it's negative, right? Positive times negative. Units miles per hour. Okay. Now, what were we asked to find? So what's the speed of the airplane? Okay. Well, what's this negative? Will we say the plane is flying at negative 500 miles per hour? No. What's the negative for? The negative is because what? It's the rate of change of x with respect to time. And what is x doing as time progresses? It's getting smaller. So dx dt is going to be negative. But the speed is going to be what? The absolute value of that. So the speed of the airplane is 500 miles per hour. And that's how a radar tracking station can determine the speed of an aircraft.